If you have polarized sunglasses, you have a quantum measurement device.
Each of these pieces of glass is what's called a polarizing filter, which means when a photon of light reaches the glass, it either passes through or it doesn't. And whether or not it passes through is effectively a measurement of whether or not that photon is polarized in a given direction.
Try this. Find yourself several sets of polarized sunglasses or old photographic filters. Look through one set of sunglasses at some light source, like a lamp, then hold a second polarizing filter between you and the light. As you rotate that second filter, the lamp will look lighter and darker. It should look darkest when the second filter is oriented 90 degrees off from the first. What you're observing is that the photons with polarization that allows them to pass through a filter along one axis have a much lower probability of passing through a second filter along a perpendicular axis. In principle, zero probability.
But here's where things get quantumly bizarre. All these filters do is remove light. They filter it out. But if you take a third filter and orient it 45 degrees off from that first one, and then you put it in between the two, the lamp actually looks brighter. This is not the middle filter generating more light. Somehow, introducing another filter actually lets more light through. With perfect filters, if you keep adding more and more in between at in-between angles, this trend actually continues. More light.
This feels super weird, but it's not just weird that more light comes through. When you dig in quantitatively to exactly how much more light comes through, the numbers don't just seem too high, they seem impossibly high. And when we tug at this thread, it leads to an experiment a little more sophisticated than this sunglasses demo that forces us to question some very basic assumptions we have about the way the universe works. Like that the results of experiments describe properties of the thing you're experimenting on, and that cause and effect don't travel faster than the speed of light. These will come into question.
Where we're headed is Bell's theorem, one of the most thought-provoking discoveries in modern physics. And to appreciate it, I really do think it's worth understanding a little of the math that we use to represent quantum states, like the polarization of a photon. And we actually made a second video showing more of the details for how this works, which you can find on 3blue1brown. But right now, let's just go ahead and hit the main points. First, photons are waves in a thing called the electromagnetic field. And polarization just means the direction in which that wave is wiggling. Polarizing filters absorb this wiggling energy along one direction so that the wave coming out on the other side is wiggling purely in the direction perpendicular to the one where the energy absorption is happening. But unlike a water wave or a sound wave, photons are quantum objects, and as such, they either pass through the polarizer completely or not at all. And this is apparently probabilistic, like how we don't know whether or not Schrödinger's cat will be alive or dead until we look into the box.
For anyone uncomfortable with the non-determinism of quantum mechanics, it's tempting to imagine that a probabilistic event like this might have some deeper cause that we just don't know yet. That there's some hidden variable describing the photon's state that would tell us with certainty whether it should pass through a given filter or not. And maybe that variable is just too subtle for us to probe without deeper theories and better measuring devices. Or maybe it's somehow fundamentally unknowable, but still there. The possibility of such a hidden variable seems beyond the scope of experiment. I mean, what measurements could possibly probe at a deeper explanation that might or might not exist? And yet, we can do just that.
With sunglasses and polarization of light. Let's go ahead and lay down some numbers here. When light passes through a polarizing filter oriented vertically and then comes to another polarizing filter oriented that same way, experiments show that it's essentially guaranteed to make it through that second filter. But if that second filter was tilted 90 degrees from the first, then each photon has a 0% chance of passing through. And halfway between, at 45 degrees, there's a 50-50 chance.
What's more, these probabilities seem to only depend on the angle between the two filters in question, and not on anything that happened to the photon before, including potentially having passed through a different filter first.
But the real numerical weirdness here happens for filters oriented less than 45 degrees apart. For example, at 22.5 degrees, any photon which passes through that first filter has an 85% chance of passing through the second filter. To see where all these numbers come from, by the way, check out the second video.
What's strange about that last number is that you might expect it to be more like halfway between 50% and 100%, since 22.5 degrees is halfway between 0 and 45, but 85% is significantly higher. To see concretely how strange this is, let's look at a particular arrangement of our three filters. A oriented vertically, B oriented 22.5 degrees from vertical, and C oriented 45 degrees from vertical. We're going to compare just how many photons get blocked when B isn't there with how many get blocked when B is there. When B is not there, half of those passing through A get blocked at C. That is, filter C makes the lamp look half as bright as it would with just filter A. But once you insert B, 85% of those passing through A pass through B, which means 15% are blocked at B. And 15% of those that pass through B are blocked at C. But how on earth does blocking 15% twice add up to the 50% blocked interact if B isn't there? Well, it doesn't, which is why the lamp looks a lot brighter when you insert filter B. But it really makes you wonder how the universe is deciding which photons to let through and which ones to block.
In fact, these numbers suggest that it's impossible for there to be some hidden variable determining each photon's state with respect to each filter. In other words, it suggests that it's not even possible for these photons to have some definite answer to the three questions: would it pass through A, would it pass through B, and would it pass through C, before those measurements are actually made. What we'll do here is a proof by contradiction. Imagine 100 photons who do have some hidden variable, which through whatever crazy underlying mechanism you might imagine, determines their answers to these questions. And let's say that all of these definitely pass through A, which I'll show by putting all 100 inside this circle, representing photons that pass through A. Now, if you want to produce the results that you see in experiments, about 85 of these photons would have a hidden variable determining that they pass through B. So let's put 85 of these guys inside the intersection of circles A and B, leaving 15 in this crescent moon section representing photons that pass through A but get blocked at B. Similarly, among those 85 that would pass through B, about 15% of them should get blocked at C, which is represented in this little section here, that's inside circle A and B, but outside circle C. So the actual number whose hidden variable has them passing through both A and B, but not C, is certainly no more than 15. But now think of what Henry was just saying. What was weird was that when you remove filter B, never asking those photons what they think about 22.5 degree angles, the number that get blocked at C seems too high. So let's take a look back at our Venn diagram. What does it mean if one of these photons has some hidden variable determining that it should pass A but get blocked at C? Well, it means that it's somewhere in this crescent moon region, inside circle A and outside circle C. Now, experiments tell us that a full 50 of these 100 photons that pass through A should get blocked at C. But if we take into account how these photons would behave if B was there, that actually seems impossible. Either those photons would have passed through B, meaning they're somewhere in this region here that we talked about earlier of passing both A and B but getting blocked at C, and that includes fewer than 15 photons. Or they would have been blocked at B, which puts them in a subset of this other crescent moon region that represents those passing A and getting blocked at B, and that guy has 15 photons. So the number passing A and getting blocked at C should be strictly smaller than 15 plus 15. But at the same time it's supposed to be 50? I mean, how does that work? Remember, that number 50 is coming from the case where the photon was just never measured at B, and all we're doing here is asking what would have happened if it was measured at B, assuming that it has some kind of definite state even when we don't make that measurement. And this is what gives us a numerical contradiction. For comparison, think of any other non-quantum questions that you might ask. Like, take 100 people and ask them if they like minute physics, if they have a beard, and if they wear glasses. Well, obviously everyone likes minute physics, but then among those, take the number that don't have a beard, plus the number who do have a beard but not glasses. Now that should be greater than or equal to the number who don't have glasses. One is just a superset of the other. But as absurdly reasonable as this is, some questions about quantum states seem to violate that inequality, which contradicts the premise that these questions could have definite answers, even when the measurements are not made, right?
Well, unfortunately there's a hole in that argument. Drawing those Venn diagrams assumes that the answer to each question is static and unchanging. But what if the act of passing through one filter changes how the photon will later interact with other filters? Then you could easily explain the results of the experiment. So we haven't proved hidden variable theories are impossible, just that any hidden variable theory would have to have the interaction between the particle and one filter affect the interaction of the particle with other filters. We can, however, rig up an experiment where the interactions cannot affect each other without faster than light communication, but where the same impossible numerical weirdness persists. The key is to make photons pass not through filters at different points in time, but at different points in space at the same time. And for this, you need entanglement. For this video, what we'll mean when we say two photons are entangled is that if you were to pass each one of them through filters oriented the same way, either both pass through or both get blocked. That is, they behave the same way when measured along the same axis. And this correlated behavior persists no matter how far away the photons and filters are from each other, even if there's no way for one photon to influence the other, unless somehow it did so faster than the speed of light. light, but that would be crazy.
So now here's what you do for the entangled version of our photon filter experiment. Instead of sending one photon through multiple polarizing filters, you'll send entangled pairs of photons to two faraway locations and simultaneously, at each one of those locations, randomly choose a filter to put in the path of the photon. Doing this many times, you'll collect a lot of data about how often both photons in an entangled pair pass through the different combinations of filters.
But the thing is, you still see all the same numbers as before. When you use filter A at one site and filter B at the other, among all those photons that pass through filter A, about 15% have an entangled partner that gets blocked at B. Likewise, if they're set to B and C, about 15% of those that do pass through B have an entangled partner that gets blocked by C. And with settings A and C, half of those that get through A get blocked at C.
Again, if you think carefully about these numbers, they seem to contradict the idea that there can be some hidden variable determining the photon states. Here, draw the same Venn diagrams that we had before, which is to assume that each photon actually does have some definite answers to the questions: would it pass through A, would it pass through B, and would it pass through C? If, as Henry said, 15% of those that pass through A get blocked at B, we should nudge these circles a bit so that only 15% of the area of this circle A is outside circle B. Likewise, based on the data from entangled pairs measured at B and C, only 15% of the photons passing through B would get blocked at C. So this region here inside B and outside C needs to be sufficiently small. But that really limits the number of photons that would pass through A and get blocked by C. Why? Well, look, this region representing photons passing A and blocked at C is entirely contained inside the previous two. And yet, what quantum mechanics predicts, and what these entanglement experiments verify, is that a full 50% of those measured to pass through A should have an entangled partner getting blocked at C. If you assume that all these circles have the same size, which means any previously unmeasured photon has no preference for one of these filters over the others, there is literally no way to accurately represent all three of these proportions in a diagram like this. So it's not looking good for hidden variable theories.
So again, for a hidden variable theory to survive, these results can only be explained if the photons are able to influence each other based on which filters they pass through. But now we have a much stronger result, because in the case of entangled photons, this influence would have to be faster than light. The assumption that there is some deeper underlying state to a particle, even if it's not being probed, is called realism. And the assumption that faster than light influence is not possible is called locality. What this experiment shows is that either realism is not how the universe works, or locality is not how the universe works, or some combination, whatever that means. Specifically, it's not that quantum entanglement appears to violate realism or the speed of light while actually being locally real at some underlying level. The contradictions in this experiment show it can't be locally real, period.
What we've described here is one example of what's called a Bell inequality. It's a simple counting relationship that must be obeyed by any set of questions with definite answers, but which quantum states seem to disobey. In fact, the math of quantum theory predicts that entangled quantum states should violate Bell inequalities in exactly this way. John Bell originally put out the inequalities and the observation that quantum mechanics would violate them in 1964.
Since then, numerous experiments have put it into practice, but it turns out it's quite difficult to get all your entangled particles and detectors to behave just right, which can mean observed violations of this inequality might end up with certain loopholes that might leave room for locality and realism to both be true. But the first loophole-free test happened in 2015.
There have also been numerous theoretical developments in the intervening years, strengthening Bell's and other similar results. That is, strengthening the case against local realism.
In the end, here's what I find crazy. Bell's theorem is an incredibly deep result, upending what we know about how our universe works, that humanity has only just recently come to know. And yet the math at its heart is a simple counting argument, and the underlying physical principles can be seen in action with a cheap home demo. It's frankly surprising more people don't know about it. Thank you so much for watching, and thank you again to Grant for doing this collaboration. This is a topic that I've wanted to do for ages and would not have gotten around to it were it not for doing this with Grant. You know, it's a longer video and his style makes perfect sense for doing something like that.
Thank you for letting me be part of this. This is definitely something outside of my wheelhouse I wouldn't usually have done.
So definitely go check out Grant's channel, 3 Blue 1 Brown, and in particular check out the second video that goes along with this one. It's about kind of fundamental math of quantum mechanics.
I mean, we just kind of want to show how the math of waves is kind of the same thing as the math of quantum mechanics, so check it out. I hope you like it. I was just going to ask you, Henry, what aspects of this project went differently from what you might have expected when we first started talking about it?
I think it took longer than I expected. Projects always take longer than you expect, but this took even longer than I expected it to be long.
Oh yeah. I don't know, part of this, I think it took long because there's Bell's theorem in particular, there's like 1,000 different ways you can go about it, right? I don't know about like the other topics you do, but usually there's like a handful of approaches you can take, and you kind of choose one, you talk with someone about it, and you go down that path.
Typically, Bell's theorem is arrived at, and the way it was historically arrived at is thinking about this kind of spooky action at a distance due to entanglement and measurements on entangled particles. And we came at it a totally different direction, which I have never seen before, and hopefully people won't be horribly angry with us for doing.
Well, so, okay, here's one thing I kind of found interesting when I was just chatting with you about, not even about this project, but you explicitly called out how you don't do like great man science, right? You don't want to highlight like Einstein is the one that came up with this, like on his own.
Right.
And this is usually a very like Einstein-y topic. So it's so tempting to like make him the main character of the video. Like, look, he was wrong in this way.
Yeah, like this video could very easily have been about Einstein making this, prediction or claim that then Bell disproved, and it's about how Einstein was wrong and Bell was right.
Yeah, right.
And we hardly even mentioned the people in the video.
But I like that.
How was it doing physics instead of math?
I mean, uncomfortable in a lot of ways because, like, they're very similar. And realistically, this topic is probably more math than physics. But nevertheless, I didn't really know quantum that well beforehand, short of like a semester in college.
Do you feel like you know it well now?
No, but I do know a lot more, right? I do feel like I have a sense for like the foundations or how things are actually described mathematically rather than just the cursory, like, here's the weird things that happen, right? Like the stuff that you'll get from like pop science outlets. Big shout out, by the way, to my friend Evan Miyazono for just helping me with a lot of that.
And I also want to say, Evan helped us actually arrive at the angle of getting into this via polarizers.
Yeah.
So like there was kind of a critical moment when the three of us were together and we were talking about this, and we said, well, it's kind of like this polarizer sunglasses thing, and we showed it to Grant, and
that just blew my. I had never seen that before. That like the 45-degree angle adds more light. Totally, like I saw that and was like, all right, that has to be the start. 100%, that's the start of the video. I also want to give a little bit of a shout out to Vince for putting the music together.
Oh yes,
right? Like remixing some Minute Physics with 3 Blue 1 Brown. That was.
I was super excited to hear that musical mashup.
Well, thanks again for letting me be a part of this and helping make this happen.
Well, likewise, this has been a pleasure.
And people, don't forget, check out the second video. Lots of fun. Lays down a little more of those foundations if you're wondering where these numbers like 85% came from.
Yeah, and you can support 3 Blue 1 Brown and Minute Physics on Patreon if you so desire. There's one other thing that I was just thinking about that now I have forgotten. Oh well.